Hello. We're on electric power technologies, and we covered coal and natural gas and hydro. And now we're looking at other renewable electric power technologies other than hydro. Hydro has been around for probably 100 years. It has been around 100 years. So now we're looking at other renewable electric power technologies, mainly wind and solar. So what about wind turbines as electrical renewable energy? Of course, they have a rotor that is rotated by the wind and generates electricity, and we extract the kinetic energy from the wind. There's been a tremendous growth in wind energy, and it makes up over between 1% and 2% of our current electrical needs. All of the U.S. wind farms are on land, such as is shown in this picture right here. Most of them are out in West Texas and in the Midwest, out in the desolate areas of the U.S. and where there's great wind. It turns out that Europe has about 50 offshore wind farms that are out in the oceans close to the shore. So I wanted to just mention those in passing. There's a lot of potential there, but the first one in the U.S. that's been permitted is up in Nantucket Sound, Massachusetts. It's been about 10 years since the developer of that has been trying to get a permit to build a wind farm out in the Nantucket Sound. That permit is now held by the developer. There are also several proposed wind farms along the Atlantic coast off of New Jersey and that area, Virginia also. So there's better wind off the shore than on land, and significantly better, and it doesn't have to be much better in order to produce a lot more power, as it turns out. And the other advantage to it is that it's closer to the large electrical users, that being the large cities. As I said, most of the land wind farms are in the Midwest, and there are not many people living in the Midwest, so they don't need much electricity out there. So they have to put transmission lines in to get the power to the big cities like Chicago or Los Angeles in order to get it to a user. The good thing about the offshore wind is that they're close to the shore, where the big cities, and New York City obviously the prime example, is that uses a lot of electricity. Now the cost, I mentioned the wind is better, so you get more power from a individual turbine, but the cost to put it out there is higher because of the water and the installation and the maintenance issues with maintaining them offshore in the water versus on the land. The major components of the turbines, of course, you have the rotor, and over here that's turned by the wind, and you have a gearbox, and the gearbox, the shaft comes in, the rotating shaft comes in to the gearbox. The gearbox slows the speed down and turns a generator to reduce the electricity. The gearbox is a major component, a major cost component of the wind turbine. And the reason for that is that the rotor only turns about 10 or 15 RPM, revolutions per minute. You can see that's pretty slow. That's one time every 4 seconds or so. But if you turn the generator that slowly, then you're going to have a very large generator. The slower generator is turned, then the bigger it has to be to produce the same amount of power. If you have a high-speed shaft and a high-speed generator, then the size of the generator is smaller in order to generate the same electrical power. So this is a major technology issue. The speed comes in at about 1500 and 15 RPM and goes out at about 1800 RPM, so the ratio is over 100 to 1 in general, and that's a major component that we don't hear too much about. But as I mentioned, the wind causes the rotor to rotate the hub, and it's just like an airplane wing. It's up in reverse. Rather than the propeller adding speed to the air coming over the propeller, it takes energy from the propeller, from the air, and turns the shaft. The blades actually, the pitch will twist, of the blades twist, and in order, depending on the wind speed. That's to maintain the maximum efficiency and to be able to extract the most energy from the wind, which the ideal pitch varies with the wind speed in order to make the rotor extraction of the kinetic energy from the wind work at its optimum rate. So it's a very sophisticated technology, and it's all automated. It senses the wind speed and decides for what pitch it needs and what RPM it needs to be rotating at, and varies it in order to stay on that optimum. Moving to solar, there's basically two kinds of solar photovoltaic installations. One is what I classified as the distributed, or example of the distributed solar power that's generally located on homes. And here's one, I believe we've seen this picture before. The solar panels are located on the roof, and the sunlight hits it, and due to a solid state phenomena converts the solar energy to electricity. You've got to watch out for shading, and you got to point the modules in the southern direction and tilt it upward. So that's one example of solar photovoltaics that we see a lot. But another one is the central solar photovoltaic farm. And in that farm, they're very large. It's exactly the same panels that are on the roof, but there are a lot more of them. And as you scale things up, things get cheaper per unit, so that generally it's a little bit cheaper per kilowatt of peak electricity that can be generated than on individual residences, where the installation is more difficult. The wiring is a lot more to each of these distributed systems. So there's pluses and minuses to each one of them. And but they're getting to be more and more solar photovoltaic farms built by utilities, since they like to have large centralized facilities like their power plants. That's what they're used to and used to building. This is another thermal technology that we just talked about, photovoltaic. But this technology is one that's been around a while, and it's a trough. It's a parabolic trough. It's linear, and there's a pipe that runs right along the focal point where the sun that comes in and hits the reflector is focused on and concentrates it and generates a high temperature in the fluid flowing through the pipe, and carries it to a central boiler that is just like the coal boiler, except again the steam is boiled with a hot fluid coming from the fluid that's heated by the solar energy. And this reflector rotates around with time of day, and depending on how high or low the sun is on the southern hemisphere, if we're in the northern hemisphere of the world. So this is one that you don't hear too much about, but there are a significant number of these out in the west and deserts, even in the U.S. This is a concentrating solar power plant. It's the same principle as the trough concept, except in this case we have mirrors, hundreds of mirrors out here, and this covers like maybe as much as hundreds of acres. Each one of these mirrors track the sun in a manner so that it reflects the sunlight up to the tower. And again, water is pumped into this tower, and all that solar energy is concentrated on that tube that's carrying the water, and it boils the steam and goes through a steam power cycle just like the coal-fired power plant, except the heat source is not combustion of coal, but the high temperatures generated by the solar energy. So I think I covered all the points here that I have listed. So those are the solar power plants and the technologies that we have. And that pretty well covers the general technology of the dominant electric power technologies that we use to get all of our electric power. Thank you.